Okay, so let's look at a graph and see what else is going to happen when we lower the vapor pressure. And so here we have alright, let's look. The original line, the original phase diagram is this sort of a light blue colored line that's kind of going up like here. So here is our normal melting point of the pure solvent. And then here is the normal boiling point of the pure solvent. Okay, when I lower the vapor pressure, I'm essentially shifting this line, this line right here is I'm shifting it down. Well, down meaning down this way, like that. Okay, and so what that does is the place where it intersects the 1 atmosphere, here and here, means that the melting point, as you can see, my melting point has decreased. My place where it intersects for my boiling point has increased. So adding a solute to a solvent will lower the freezing point and will increase the boiling point. Okay, so here are our expressions for the change in the freezing point is equal to this freezing point constant times the molality, and this is the molality of the particles, and then this is our boiling point constant, and both of these constants are based on what solvent you have. They are particular to the solvent, whereas our molalities here is the molality of the particles of solute. And so here's a table. You have a similar one in your book that gives some values for the normal freezing points, your freezing point constant, and your boiling point constants. Okay, so let's take a look at an example problem here. Here I have, I'm adding glycerol to water, and we're going to dissolve 46 grams of the glycerol, which has a formula weight of 92. So 92 grams in 1 mole. So that's 0.5 moles of my glycerol. And it's dissolving it in 250 grams of water. All right, we're doing molality. So that's 0.250 kilograms. So my molality is going to equal 0.5 moles of glycerol per 0.25 kilograms of water, which is going to equal 2. Okay, and then we want to calculate the boiling point of the solution, an atmospheric pressure of 1 atmosphere. So my normal boiling point, which since we're at 1 atmosphere, it's normally going to boil at 100 degrees Celsius, because this is for water is our solvent. And then for water, if you look that up, our KB is going to be 0.51, and the units on that are delta T per molal. All right, and this is glycerol is a non-electrolyte, so we get 1 glycerol molecule per 1 unit. We're not dissociating any, it's not ionic. So our delta T boiling is kb. So my molality is 2, and then times 0.51 is going to give me 1.02 is my delta T, and so my boiling point of my solution is the original boiling point of the solvent plus the delta T from the solute. So 101.02 degrees Celsius would be my new boiling point. Another type of problem you'll see is where we have the data for the boiling point elevation or freezing point depression, either one, and we want to calculate what the molar mass is for some unknown solute. And so here it says we have 14 grams of our solute, and we have 1 kilogram of benzene, that's our solvent, and it says that our boiling point of my solution is 81.7 degrees Celsius. And what I want is the molar mass, which, remember, units, grams per mole. Okay, well, I know my grams. I have 14 grams of my solute. So what I need to know is how many moles does that relate to given this information? Well, we know that our change in the boiling point is the molality times the boiling point constant. And for benzene, let's see, what's our information we have? Benzene, the normal boiling point for this is 80.2 degrees Celsius, and the constant is 2.53. Okay, you can look these up. This benzene is in your table in your book. Okay, and we know that our boiling point of our solution is going to equal the normal boiling point plus delta TB. Okay, so we have a value for this and we have a value for this. Okay, and so, and for this, let's see, we have 81.7 and 80.2 was the original, and this is equal to the molality times KB. Okay, and 81.7, so that's 80.2 plus the molality, and my KB is 2.53. So let's simplify that out, and we're going to solve for our molality. And when we do that, we get, let's see, 81.7 minus 80.2, and then divide by 2.53. And I'm getting a molality of 0.593. Now, so what are we going to do with that? We need moles, not molality. Well, let's refresh our memory on what molality is. That means 0.593 is equal to moles of the solute over kilograms of solvent. Okay, I know how much benzene I use. 0.593 is equal to moles of solute over 1 kilogram. So 0.593 is equal to moles of the solute, and that value is what I need right there. So when I divide that out, 14 divided by 0.593, I get 23.6 grams per mole.